Welcome back to class, everyone. Today, we are diving straight into a new explainer, and we're getting small. Really, really small. We're talking atomic scale. We're going to explore how the absolute tiniest building blocks of reality actually end up shaping our massive, chaotic universe. Just to put this scale into perspective, a single strand of your hair, yeah, that's about 1,000,000 carbon atoms wide. Mind-blowing, right? Anyway, I'm absolutely pumped to guide you through this today. Let's get into it.
Grab your notebooks, because here is our lesson plan for today. 1. Meet the atom. 2. Decoding atomic numbers. 3. The secret of radioactivity. 4. Alpha, beta, and gamma. And finally, Section 5, radiation in our world.
All right, Section 1, meet the atom.
So let's start with the atom itself, the fundamental unit of, well, literally everything. Your desk, your coffee mug, the air we're breathing right now, it's all built from these guys. If you picture the fundamental planetary model on screen, you've got this incredibly dense, tightly packed nucleus right in the dead center. And then, zooming around the outside, are these distinct energy shells. It actually looks a lot like a tiny little solar system with planets orbiting a sun.
Now, inside every single atom, you've got 3 main players. And for those of you taking notes for the exam, you're going to want to remember exactly where they live and what charge they carry. In that central nucleus, you've got heavy, positively charged protons tightly packed together with neutral, uncharged neutrons. Now, since positive charges naturally want to repel each other, you can kind of think of those neutrons as the vital glue holding the whole nucleus together so it doesn't just fly apart. Meanwhile, on the outside, those lightweight, negatively charged electrons are zipping around in those energy shells at literally mind-boggling speeds, perfectly balancing out the positive charge in the center.
Moving on to Section 2, decoding atomic numbers. Okay, so how do physicists actually read and classify these things? We use a standard atomic notation, or what's sometimes called nuclide notation. We'll use carbon-12 as our gold standard example here. When you look at the periodic table, you'll see a chemical symbol, like C for carbon, flanked by 2 very specific numbers. Think of this as the universal shorthand of nuclear physics.
Please don't get these too confused on the test. The nucleon number, which we represent with a capital A, is your mass number. Basically, it's the total sum of both the neutral neutrons and the positive protons hanging out together inside the nucleus. It tells you exactly how heavy the atom is. On the flip side, the proton number, or Z, only counts the protons. That number is absolutely crucial because it defines what element the atom actually is. Oh, and here's a little cheat code for you. In a perfectly neutral atom, your proton number is going to match your exact number of orbiting electrons. Easy, right?
All right, let's turn the page to Section 3, the secret of radioactivity.
So imagine a tiny, incredibly crowded room where the structural balance is suddenly just thrown completely out of whack. What actually happens when a nucleus has too many, or maybe too few, neutrons? Well, that nuclear glue we talked about earlier, it fails. The atom becomes totally stressed out, jittery, and entirely off balance. It basically turns into what we call an unstable isotope.
When an isotope gets unstable like this, it desperately wants to fix the situation and find some peace. So what does it do? It spontaneously decays. It achieves stability by literally chucking out extra particles and radiating away all that pent-up excess energy just to get back to a comfortable, balanced state. And that physical emission of particles and energy, that is exactly what we call radiation.
But here is the truly wild part about all this atomic drama. Radioactive decay is completely random and spontaneous. That means the process is totally unaffected by external factors. You could apply extreme heat, intense pressure, crazy chemical reactions. Doesn't matter. We cannot predict exactly when the next emission is going to happen or how much energy will be released. It happens entirely on its own schedule, completely outside of our control.
Which brings us to Section 4, alpha, beta, and gamma.
Consider this table your absolute cheat sheet. We've got 3 main types of radiation, and their mass dictates exactly how they behave. Alpha particles have the biggest mass, which means they act kind of like bowling balls. They just crash into everything. This gives them the highest absorption rate, but the absolute lowest penetration power. Seriously, a basic piece of paper can stop them. Beta particles, they sit right in the middle. Medium mass, medium absorption, and a relatively short penetration range in the air. And then we have gamma rays. Gamma has literally 0 mass and the lowest absorption, but highly powerful penetrating abilities. You'd need thick blocks of solid lead or concrete to safely stop a gamma ray. Now you might be wondering, how do we even measure this invisible energy? Well, we use a device called a Geiger-Müller tube connected to a counter. You know that famous click, click, click sound you hear in movies? That's the one. The process is elegantly simple. First, ionizing radiation enters the tube. Second, it collides violently with argon gas particles sealed inside. Third, this intense impact physically knocks electrons away from those gas atoms. And finally, that knock-loose electron conducts electricity, creating a measurable pulse of current. The machine basically just counts those tiny electrical pulses, giving us a real-time rate of the radioactive decay happening right there in the room with us.
Okay, let's zoom back out for our final section, Section 5, Radiation in Our World.
It's super important to remember that background radiation isn't just some sci-fi concept locked away in a high-tech lab. It is totally normal, and it surrounds us constantly. Check out this breakdown. A massive 50% of it comes from radon gas, naturally seeping right up out of the ground. It also comes from everyday building materials, cosmic rays zipping down from deep space, and get this, 15% of our everyday exposure comes directly from our food and drinks. Bananas, for instance, they're famously a little bit radioactive because they naturally contain potassium.
And because those gamma rays we talked about earlier have such incredible penetration power, we can actually harness them for some amazing practical uses. For instance, we use them to safely sterilize food as it moves along a factory conveyor belt. It kills off the harmful bacteria without actually making the food itself radioactive. In heavy industry, gamma rays act almost like a super-powered X-ray. We use them to inspect the deep structural integrity of massive metal welds, which ensures that our bridges, airplanes, and pipelines are completely safe and secure. But arguably, the stakes are the absolute highest in medicine. We rely incredibly heavily on atomic decay to perform life-saving procedures. Radiation is absolutely critical for treating certain cancers through specialized therapy, where it actively targets and destroys harmful cells. It's also used to generate highly detailed diagnostic imaging from inside the human body. It's truly a cornerstone of modern medical science, working right alongside its vital roles in agriculture and scientific dating.
As class comes to a close today, I'm going to leave you with a bit of a puzzle to think about before our next explainer. Put yourself in the shoes of a doctor utilizing radiotherapy. How do you go about harnessing a radioactive isotope with the absolute perfect half-life? Think about it. It needs to be long enough to properly complete the internal investigation or treat the patient, but short enough that the radiation doesn't stick around in the body and actually cause harm. Chew on that, review your notes, and as always, stay curious.